Okay, grade 12. This is my third attempt. My computer has been glitching, or the software just doesn't work very well with this computer. I don't know what's going on, but some stuff happened with the files. So it's been about 20 minutes now. So I'd like to continue with the lesson number 2, which is on chapter 10, galvanic and electrolytic cells. And there is some stuff in that chapter that we're not going to cover, some stuff or material that I've included in the package that we just don't have time to cover this year that would have been enrichment, but we're going to stick to our guns, stick to the basics of what is in the textbook. So if I'm going to share the screen right now, and hopefully this is going to work this time. Okay, there we go. That is the file that we're working on. Galvanic cells was the topic last time, and we took a look at the physical setup of a galvanic cell. With a galvanic cell containing a spontaneous redox reaction. In other words, a redox reaction where the sum of the voltages for the oxidation half cell plus the reduction half cell is greater than 0. It is positive. If it's negative or 0, then you have a different kind of cell, not galvanic. And we took a look at the bits and pieces, the parts of that physical setup, and what they're actually doing and what was going on. So we did a fairly in-depth analysis, but we stopped short of the very last point in section number 1 on this page over here. We didn't do line diagrams or how you represent a galvanic cell or how you represent any kind of electrochemical cell. And I stopped there because there are a number of different setups that I'd like to go through with you. We went through one setup last class, so it would be this one right over here, a galvanic cell. You can see at the top again, the E0 cell, the overall voltage, the sum voltage for the cell is greater than 0. And the physical setup where you have the oxidation half reaction, oxidation half cell separated in space, physical space in beakers in a crude setup into 2 different spaces separated from the reduction half reaction half cell. But to complete the circuit, as you know in electricity, everything must be connected by a conductive material or a medium that allows electricity to flow through, either electrons or ions to flow. So connecting the beaker on the left to the beaker on the right, you have an electrode, which is a solid electrical conductor in one, an electrode, solid electrical conductor in the other, and then these alligator clamps that attach to both of those electrodes, and a metal wire that allows electrons to flow through the wire. In other words, electricity to move from one to the other. But you still have the space in between the 2 beakers where there is no wire, so you need some other kind of conductive medium or conductive material to allow electricity to flow through the other. So you have this upside down glass tube, hollow glass tube over here, plugged with cotton on the left end, upside down over here, and the right over here, and it is filled with an electrolytic solution that allows electricity to flow through. So electrons will not be flowing through the salt bridge, this upside down U tube, the electrolytic solution, but the positive and negative ions are able to migrate in opposite directions. And as long as you have moving charge, whether it's moving charged electrons or moving charged ions, big or small, that constitutes, or that is by definition, electricity. So you have a salt solution, a medium that allows electricity to flow through it, versus above that, a wire which allows electrons to flow through from atom to atom, metal atom to metal atom directly. And then you have a complete circuit connecting all, this is a series circuit connecting all components within this one galvanic cell, with those electrons being energized going from one cell to the other. Okay, so in this particular setup of a galvanic cell, you have 2 separate beakers where the 2 half reactions are occurring in separate spaces. In other galvanic cells, those 2 half reactions can actually occur within the same beaker or within the same physical space, and you can actually still get a voltage. So I'm going to scroll down to this over here, to the next page, the next page, to 3 more setups where over here, look, you have 1 beaker on the very left-hand side with 2 electrodes that are different, connected by a full circuit, and this entire redox reaction occurs in that one same solution, and you get a voltage. The middle voltage, the middle setup for the galvanic cell above. Gallifrey, sorry, that's my dog barking. Gallifrey, come here. Come here. That's enough. You don't have to bark at everyone that goes past the house. Sorry about that. So the middle setup above is the setup that we saw last time and again earlier today in this video. And the third setup you'll see down here in the bottom right, where again it looks like you have the entire redox reaction occurring in the same beaker, and you do, but you actually create a second compartment within that one beaker using this. You can see this is like a hollow. It's called a porous cup. It's basically a hollow ceramic tube. It is a ceramic at the bottom, so it is a ceramic cup. And inside this ceramic cup over here, you have the solution for one of the half cells, and the solution outside this hollow porous cup, a ceramic cup, is the reaction for the other half cell. You have one electrode inside with the one half reaction, and one electrode outside in the beaker for the other half reaction, and then you have a full circuit. So basically this porous cup allows electrolyte to flow in and out, solution to flow in and out, and it replaces a salt bridge. And it's a simpler setup. We could do this, so we had all the materials to do it at school, but unfortunately we are not going to do it. And then you get a voltage. And then you can see underneath each of these physical setups or pictures, there is AG, there are these vertical lines, and then you see from left to right, there are chemicals written from left to right. This is referred to as the line notation for electrochemical cells, whether it's a galvanic cell or an electrolytic cell. And you can see that in all cases on the outside left and the outside right, the outside left and the outside right, the outside left and the outside right, you have your electrodes located. Okay, so what is the setup for these for this line notation? This is where I go to the other mode, tablet mode, and this is where I had to end the video. This is the third attempt, so hopefully it won't happen again. Oh dear, here we go. Yes, it looks like it's working. Okay, now insert draw. Okay, green over here. So line notation for galvanic cells is the way of representing galvanic cells. Okay, and we start with the oxidation half cell on the left-hand side. Oxidation. Okay, half cell on the left. And then you have over here a physical barrier represented by a double line over here. That is the physical barrier between the two half cells. And then you write the notation for the reduction half cell to the right of that physical barrier, or that double vertical line. Reduction half cell. Okay, so what is in the oxidation half cell? Well, on the very left-hand side, you start with the anode, which is the negative electrode, and then the anode is a solid electrical conductor. So there is a phase boundary between the solid and then the aqueous solution surrounding it, and that phase boundary is represented by a single vertical line like that. And then you write the solution that constitutes the reactive chemicals in the oxidation half reaction, so electrolyte. Over here for the oxidation half reaction, and then that is the oxidation half cell, and then we move to the reduction half cell. And inside the reduction half cell, you have electrolyte. And part of that electrolyte contains the reactants that constitute the reduction half reaction occurring in the reduction half cell. And then inside that electrolyte or reduction half cell, you have a solid electrode called the cathode that is separated. There's a phase boundary between the electrode and the solution surrounding it, represented by a single vertical line. And then you write cathode over here. And that is the setup. Okay, so this whole thing is the oxidation half cell. Oxidation half cell. That noise is my wife's copy machine turning off. And this whole thing over here, when you write it with the actual chemicals, is the reduction half cell. Okay. Okay, so what is an anode? Okay, it is a solid conductor. As I said last time, or in the last video, the anode might actually be a reactant in the reaction, but if it is not, we call it an inert electrode, such as platinum solid or graphite solid, carbon graphite. And the cathode is also a solid conductor. How do you choose a solid conductor? Well, you look at the reaction, and sometimes you have a conductor that is a solid, and it's a reactant that is part of the oxidation half reaction. Same idea for the reduction half reaction, and then those materials become the anode and or the cathode, but not always. So what is included in these electrolyte solutions over here? Well, I'm going to tell you that your textbook says, and all textbooks generally say that these are electrolyte solutions. However, there are sometimes non-electrolyte chemicals that actually need to be written in here. So essentially, I'm going to say that these are lists, or basically you list, okay, your reactive chemicals. Okay, so they may be ions, molecules, okay, or ionic compounds, you will hopefully see. Okay, and this over here is, okay, this thing over here, if you don't recall me saying 2 minutes ago, is a physical barrier. Okay, between the two half cells, the oxidation reduction half cells. For example, it could be the salt bridge, okay, or it could be the porous cup, okay. And if the entire redox reaction occurs in the same beaker or the same compartment, the same chamber, then you do not include that vertical double line. And then that is that. Okay, so over here, look at this. There's one version over here. Oh, and the other thing is this. Oh, and it says it over here. I'm gonna just highlight that. Okay, highlight. Electrons flow in this direction. Okay, let me write that over here in green. Okay, note, electrons flow from from the anode to the cathode. So from the negative electrode to the positive electrode, where they're lost to where they're gained. Okay, and know the direction of electron flow. Okay, so that's the setup over here, and then let's look at line notation over here. Line notation for the galvanic cell, where the entire redox reaction occurs in the same beaker. Look over here. So this is a look at this vertical line over here. This vertical line represents the phase barrier between the anode, and this is the cathode. Okay, and oh, why did I do that? Okay. Anode, this is the cathode over here. Okay, and over here, this is the anode, and this is the cathode, and this is the porous cup. Porous cup is represented by this thing over here, and this one over here, that notation is the same as what we saw for our own over here. Okay, so let's move on to some new material over here. Okay, and over, I don't know why it moved that all the way down over here. I'm going to delete that. I'm glad it didn't do it for everything else. That's the issue that I had last time. Okay, so over here we have, it's not allowing me to do Okay, there we go. Okay, so we have over here in this diagram, two galvanic cells in series. If you have two galvanic cells in series and one has a voltage of 1.5 volts and the other has a voltage of 1.5 volts, okay, VT is equal to V1 plus V2. That's grade 9 material, which equals, well, 3.0 volts. Okay, so you can add the voltage of multiple cells in series and you end up getting a higher voltage. And that's actually what happens when you create a battery. You have multiple cells, electrochemical cells, placed in series within your battery to give you your 1.5 volt battery. Okay, so now we are going to deal with some of these questions over here. And I feel like I should have something over here, missing a page. Okay, let's stop recording. Oh, here we go. Okay, so I'm back. So I had to stop the video for a second or a minute or two there to find my sheets. I'm going to stop sharing this and have you refer you to this sheet right over here. Share screen. Hello. Okay, where is it? Okay, so apparently I can't share it. In any case, it is the, see this sheet right over here. The table of standard reduction potentials. Oh, why didn't I think of this earlier? So here's some practice questions. It says, in each pair of substances, which substance is more easily oxidized? Okay, more easily oxidized. So you're going to be looking at all of these oxidation half reactions for lithium versus potassium. More easily oxidized means loss of electrons. Okay, where do you see the loss of electrons? It is the reverse reaction in the table of standard reduction potential. So if you go from the right-hand side, read it backwards, read it towards the left-hand side, those are oxidation half reactions. So reverse half reactions in table of reduction potentials. Okay, and the E naught oxidations equals the negative value of the E naught reductions. Okay, so the negative value. So the E naught reductions, these values over here are the voltages in the table. So if we make them all negative, make the positives negatives and the negatives positives, and the zero stays the same, then we'll have oxidation potentials. So what is the oxidation potential for lithium? Well, lithium is down at the very bottom. It is the very bottom one, very bottom corner over here. I'm not sure if you can see that. Very bottom right-hand corner, bottom right of that table. Lithium, okay, and it has, look over here, the least it has the most negative reduction potential. That's the lithium positive 1 ion. That means the lithium solid, reading it backwards, Li, changing into Li plus E minus, has an E naught oxidation. Oh dear. Has an E naught oxidation, which is equal to positive, not negative, positive 3.04 volts. Okay, whereas K plus, K changing into K plus an electron. We read that one backwards. Where do we have it? Let me find potassium. It is, okay, where is it? K plus, oh yeah, it's right above it. It has an E naught ox, which is equal to positive 2.93 volts. Okay. Now, which is more easily oxidized? Well, the substance that has the higher positive oxidation potential is more easily oxidized. That process happens more easily. So lithium would be the answer. And in fact, since lithium has the most positive of oxidation potential of all of these substances that can be oxidized in your table, lithium, in fact, is going to be more easily oxidized than any of the others. Okay, so that means that over here, I can say that all of these substances, okay, E naught oxidation is less than positive 3.04 volts, okay, for all these substances. Okay, that means they will be oxidized with more difficulty than lithium metal. Okay, what about copper? Oh, sorry, I shouldn't have gone all the way down here. Okay, that doesn't include that one right there. So that includes only up to gold over here. So now going down to copper or silver again, which has a greater positive oxidation potential. Well, copper does. Between silver and H2O. Sorry, that should be a subscript H2O, the 2 in the H2O. This one over here, between copper and H2O, copper is more positive. Between nickel and H2O, so you're looking at what the H2O on the right-hand side, find it. The Ag on the right-hand side, find it in the table, which has a more positive oxidation potential, so reverse the reduction potential. And that's what we're getting over here. Okay, so copper versus Ag versus H2O, and now over here, copper versus H2O, nickel here, zinc has more positive, and gold versus H2O, H2O is more positive. And now here is a thinking question. Well, why are halogens so dangerous? So this has something to do with your understanding of what oxidation means and what is going on with oxidation, and ease of oxidation and difficulty with oxidation, ease of reduction, difficulty of reduction. Oxidation reduction occur within reactions. So the more easily something is oxidized, basically you're saying the more easily it reacts. If something is very easily oxidized, it will likely react very, very easily. So when I ask the question number 2, why are halogens so dangerous? Sorry, I'm just looking at the time. I thought for a second that the video would stop. Why are halogens so dangerous? Well, halogens are very strong. Halogens themselves, F2, H2, Cl2, Br2, they become reduced. Okay, i.e., they are oxidizing agents. Okay, if they cause something else to be oxidized, And in fact, they are very strong oxidizing agents. How do you know? Well, you know because they become reduced very easily. They have high, relatively high to very high reduction potentials. Okay, they have very high reduction potentials or voltages, i.e., this indicates they become reduced very easily. Okay, and another way of saying that is that they are very strong oxidizing agents. Okay, so they cause most other substances to oxidize. To oxidize. Not all. Okay, so that is to react. They cause most other substances to oxidize or react in such a way that those other substances will lose electrons. Okay, and when something loses electrons or gains electrons, it is no longer itself, it becomes something else. It's destroyed. And they will basically cause the oxidation of just about anything they come into contact with. That's why you don't want to ever be around these halogens, okay? They're so dangerous. Okay, and there are a bunch of questions over here, which you should try. Okay, now I'm going to, I have a bunch of packages here with stuff in them. We are at 27 minutes, so I'm going to stop this recording and then I'm going to go on to the self-potential problems in another video. Okay, I'm going to stop share over here and bid you farewell. Okay, do your best to keep up with that. So that's there's not a lot of problem solving right there. That's more housekeeping and notation, but these are skills that you have to be good with from electrochemistry. And I know that a lot of other schools and programs, they sort of just glance through electrochemistry because they don't think it's core chemistry. But if you take first year chemistry, you will do it again next year. And you'll do it in this kind of detail, and you'll have to figure it out on your own. So certainly refer back to this material, make good notes, learn it as best you can with everything that's going on around you, as I've said many times now. And the more you learn, the better off you'll be next year if you're going to take it again. Okay, so I'll end the video there, and I will be back.